Week 13, Part 1, Simple Magnifiers. When Sherlock Holmes uses a magnifying lens, he tends to use it like this. He puts it right up to his eye, and then he can bring the object very, very close. Let's take a look at how this magnifies things. So I need to share my screen. And this is going to be a PowerPoint. I'm trying to figure out how to do that. So when you hold an object close to your eye, it subtends an angle. So right here is the angle that this object that is of height h is creating at your eye. So we say it subtends the angle alpha 1. And let's imagine that you're holding the object as close as you can and still be able to focus on it. At a certain point, you can't focus anymore, and so you're right at what we call the near point of your eye. Then if you instead use a magnifying lens, it turns out you can hold the object much closer and still focus on it properly. And that's the main advantage of using the magnifying lens. It doesn't so much change the angles of the rays coming in as it makes them parallel so that you can focus on it while holding it much closer. And so you can see in the second case, the angle is much larger at your eye. The angle subtended by the object has become larger. So if we do the math over here, in the first case, alpha 1 just depends on the size, the height of the object, h, divided by how far away it is, and that would depend on the near point of your eye. For the purposes of naming magnifications and such, there's a standard distance that's 25 centimeters that's used. Probably all of you have a near point that is quite a bit shorter than that, probably less than half of that. Most of you have 10 or 11, something like that, when you're college age. As you get older, that number gets longer and longer, and you have to keep holding things further away. And eventually you can't tolerate that, and you have to get bifocals or reading glasses or something. But this is the number that's just used as a way of standardizing what we consider sort of an ordinary near point. It's really a fairly old near point. Now, when you hold the magnifier close like this, physics textbooks always define this in the case where you hold the object right at the focal length of the lens. That means that the rays that come from here end up going parallel into your eye. And so your eye sees these rays as if they were coming from infinitely far away. So the object seems to be infinitely far away, but also sort of infinitely tall. And it still just has a well-defined angle, alpha 2. But the fact that you're doing that means your eye is resting. Your eye is in its most comfortable state for looking at an object long term. So that's the easiest thing for your eye, and that's what any scientist who wants to work on something long term, you need to be setting up your optics so that your eyes aren't straining right at their limit. So in that situation, if you're right at the focal length of the eye, then we can define the angular size of the object as just h over f. That angle there is h over f. This is defining these angles in radians, and using also the small angle approximation. The angle would really be sort of a curved h over alpha. Alpha would be h over this distance, but only if h was measured along the curve. But we're going to ignore that point and just measure it this way. So if these are the two angular sizes, we would hope this one would be larger, the way I've shown it here. But the magnification then would be the ratio of these two. How much bigger is alpha 2 than alpha 1? So that's what I take here. Find the magnification as alpha 2 divided by alpha 1. This is a capital M instead of a little m because we're finding the angular magnification, how much this angle has changed, as opposed to how much different is the size of h somehow. Here the h is the same in both cases. So if you take this ratio, you find it's just 25 divided by f. So whatever the focal length f is, that you can use that in this formula. And that's our physics definition of the magnification of this lens. Now you might wonder, if that's our physics definition, that seems a little strange because you could have a lens whose focal length is 25 centimeters, and it would be a positive lens. It would, in fact, seem to magnify things, and yet this would tell us that the magnification of such a lens is 1, as if it didn't do any magnifying at all. Well, that's very strange. But actually, that's just because of the way you're using it. It's just a matter that we're using some of the magnifying power of the lens in order to relieve eye strain. And what's left, we get this magnification from. But if you don't have a very strong lens, that's all you get out of it, is a little bit of relaxing of the eye. On the other hand, if you're in the business of selling magnifying lenses, especially to the general public, you never use this formula. What they always use is what magnification can you get at maximum eye strain? How big a number can you get? I won't bore you with all the math. It's not so terribly difficult, but the answer is extremely simple. You just get 1 higher than whatever you got with this. So say you go through this formula and calculate that the magnification of a lens is 2.5, then the common magnification that anybody would quote if they're selling these lenses would be 3.5. So I just call that common magnification and physics magnification. No physics books ever mention this second one, but it is the one that is always used out there in public when you buy or sell magnifying lenses.